Welcome to Unlocking Direct Current, very vast program. And today is a very expert topic with voltage standardization for DC microgrid success. We are thrilled to have you here today. I see the list of participants building. Our hosts are Paolo Catapane, who is product owner of microgrids at ABB, and Harry Stokman, who is a DC expert, chairman of the DC expert company and founder of the DC Foundation in the Netherlands. Both are valued partner of CurrentOS, so CurrentOS is very happy to have them today to host this webinar. And I am Raphaël Raymond. I am responsible for marketing activities at CurrentOS. Before we dive in, I have a few housekeeping notes for you. So this webinar is being recorded. We can send you the recording via LinkedIn. You just send us a message and we will also post it. We have plenty of time at the end of the webinar for Q&A. So ask your question in the chat along the presentation and we will answer to them at the end. If your camera is disabled and you would like to ask a question, please turn it on so we can see who was asking the question and we can interact at the end. Don't forget to follow CurrentOS on LinkedIn. It's a great way to stay connected with our vibrant DC community. And maybe I will start with a few words about CurrentOS for those who are new to us. So CurrentOS, we are a non-profit organization defining standards for direct current microgrids. Our mission is to empower a sustainable future by providing reliable electricity access for all. And we are a partnership. You can see here the list of our partners. We welcome manufacturers, integrators, universities, certification bodies, trade groups. Currently, we have over 65 partners across 22 countries. It's a very wide ecosystem. Everyone is welcome. Is welcome to join to get access to the IP and to collaborate. We try to have a very collaborative organization. And the board members today are ABB, Eaton, Schneider Electric, Stridonic, and New Solution. And the board is meant to grow. Additionally, last thing that's not on this slide that I will add is that we are a liaison A status with the IEC, with the LVDC, SIC LVDC of the IEC, which is really reflecting our commitment to international standardization effort. And standardization is the topic of the day. So now, without further ado, I will turn to Paolo and Harry. Over to you to start our discussion today.
Okay, thank you. Thank you very much, Raphael, and thanks to all of you attending today this webinar series. So today we will focus on some specific aspects of the DC microgrids, which CurrentOS is promoting and pushing. And we are going to explore the topic of the voltage within the set of rules which CurrentOS has been developing for the DC microgrid systems. Just for the sake of clarity and introduction, the typical installation of the DC microgrid we are referring to is a DC microgrid where you may have loads, you may have batteries which can behave in different manners. You have photovoltaic, you have loads, and you have a converter interfacing to the microgrid, to the grid. So the set of rules is a document which has been prepared to describe how the system works. And if we move to the next slide, we would like to highlight why CurrentOS was developing a set of rules. What is the spirit behind the set of rules? So to understand that, we need to start from the challenges that CurrentOS would like to solve in the context of the adoption of these DC installations. So there is a number of things we would like really to overcome, which you see on the left-hand side, which are ranging from overcoming DC safety concerns but going in a wider manner, we would like to build a multi-vendor interoperable systems. And at the end, we want to simplify life of building stakeholders who are involved into the crucial phases of designing and building those DC microgrids, with the final target of scaling up the adoption of those installations, because at the end we believe all the partners that this type of installation will promote and support the energy transition and ensure resilience and flexibility. So this is the forward and the reason why there is a set of rules, which practically speaking translates into the aspects which you have on the right-hand side. So there are technical things and technical points which need to be addressed. And you see the main ones here on the right-hand side. So the control, the protections, the isolation between DC and AC, the earthing, the pre-charging and corrosion are all aspects which are fundamental in designing and implementing this type of systems. And today we would like to focus on the first bullet, so the voltages. And now I'm asking to Harry, why we speak and we focus on voltages in DC?
Yes. Thank you, Paolo. Yes, I can answer that in a very simple way, but I want to say something because if you discuss something about voltages, it's a very emotional topic actually in a technical domain. People are very fanatic, and there are many voltages pushed into the world, and to be a candidate to become a standard. But the difficulty is always that everybody is selecting a voltage that is suitable for that application. And if things are suitable for an application, you want to push it, but yeah, you have to find compromises. And that's why it's so important to find the consent on the voltages, because if there is no consent on the voltages, it's then it is very difficult to open the market. So for DC, particularly for systems like current OS, or to make DC a wild open system to use in many different applications, okay, then it's incredibly important to find that consent and to open the market. And that is what we try to do in current OS. And that's why it's so important. And that's why this is one of the key topics to address first before it comes to the other items. Is that answering a little bit the question, Paolo?
It is. So it's really a key topic.
Yes.
Sorry, thank you.
So, yeah.
Yes, I'm ready for the next.
Paolo, can you say something about how the system is reacting to voltages?
Yeah, okay. So this is moving into another direction and a very important aspect. In the current OS type of installation, we are talking about voltage bands. And there is a very specific reason for that. Let me start from AC. AC as a parameter which is mirroring and giving us the indication about instantaneous equilibrium between generation and demand, which is frequency. So in AC systems, if we look at frequency, we have a feeling if we are meeting the instantaneous balance between generation and demand. In DC, in this type of networks, where we have a certain type of distributed control, this parameter is the voltage. So you may have participated to a previous webinar where we already presented the voltage drop type of distributed control that we promote within current OS. But to summarize, in this type of networks, the voltage indicates if there is an equilibrium between the demand and the generation. So essentially, there is not a nominal value, but there are bands within which the system can operate. So if we take the nominal band, and there you see the nominal values 350, 700, and we will explore later why specifically those values. Within the nominal band, if the system is operating in one of those points, it means that substantially there is equilibrium. If the voltage goes down, it means that there is more load than generation. And so you have different levels going down where certain loads will start to disconnect, and you prioritize through the voltage group the most essential and critical loads. On the other hand side, if you have a voltage which is going up, it means that you have more generation. So when you have more generation, you can, for example, charge your batteries or export to the grid. So these voltage bands are the ranges within which the system can operate. And now, an important point where I would like to ask Harry's help here is to understand which are the cornerstones or the key elements when choosing the voltages, because here we are saying 350, 700, but which are the critical aspects which are important to consider when choosing those values? So can you bring some clarity around that, Harry?
Yes, of course. And that is a little bit to go back to the basics. Like in AC, we have a three-phase system as a neutral. And there we know, for example, when you have the line voltages, line to line is, for example, 400 volt in Europe. And when you have measure line to earth, it's 230 volt. So that means if you build a three-phase system, you always have the square root of 3 that is between the different voltages within the system. In DC, you have two possibilities. You have what we call the unipolar system. That means, okay, it's only 2 lines, and there you have the voltages. But when you have a 3-line system, and then you introduce a midpoint, then actually you have, compared to AC, a 180 degrees phase shift. And that means that the voltage is just in the reverse direction. So that means normally in DC you will have a plus and a minus and a mid. And that means, like in the case of current West, 350, that means if your mid to line is 350, then you have to double 700. And this is important because in low voltage area, we have a limit, a hard limit in the standardization where we talk about 1500 volt. So if the doubling is the rule to define the voltages, then you have to make sure that you can utilize the full band what is available in the low voltage domain. Just to make a small example, if you select, for example, 400 volt as the nominal voltage in the system, and you go for a doubling because you want to have a bigger system, then you can have plus or minus 400, makes 800. But again, if you want to expand the system to a bigger system even, then you want to go to plus or minus 800. And that doesn't fit into the low voltage band because then the nominal voltage is 1500 volt. So you have to be smart to define the labels in a way that they fit into the 1500 volt band and that you can use the doubling of the nominal voltages to fit and to utilize the full band. So this is why it's important to understand unipolar and bipolar and the 1500 volt band. So, and Paolo, back to you. As how does a current West system looks like in common practice?
Yeah. Thank you, Ari, and we can move to the next slide. And here,
sorry.
You can see how it is.
I will finish my story. Yes, and this is how to say. This is a very important topic because it comes to earthing, and earthing and voltage definitions are very strong related. And to give just a small example, if you like in unipolar systems where you have an TNS, because unipolar only exists in TNS, as you see here in the pictures, because the bipolar system is defined in the IEV, in the IEC, that it is 2 different voltages against PE. That means when you have a plus and minus, and you are, for example, in IT, then the IT system is a bipolar system because it has 2 different voltages against PE. So And normally, if it's a balance, then, for example, if you have a 350 volt IT system, then you measure between the lines 350, but you measure against the PE, you measure 175 if the system is properly balanced. And that's why you consider it the bipolar. So the only unipolar systems exist is in a TNS, where you have just one of the conductors ground. And one topic I want to add a little bit to think about it, because I think earthing is a complete topic on its own. And I think we need to have a webinar about that one, probably 2 hours, because this is a huge topic to discuss. But I want to say in DC, because people are so well known in AC, and you know everything. And in AC, L1 and L2, L3 are the same line conductors. There is no differences from how to say the behavior against PE. But in DC, L minus or L plus are totally different conductors. So the sign, the positive and the negative sign, has a huge different effect. So you can even compare it like your bank account. A positive number is totally different than a negative number. So that means that in DC it's the same. So, and to give a small example, in TNS systems, in unipolar systems, in telecom, it was often used to have a minus 48 volt system. And that is because the negative conductor is different than the positive conductor. And the reason why they use in telecom, for example, minus 48 volt, was because of corrosive effects on the electrical insulation. And that's why in current West, for example, we say, okay, we like to have a positive system to PE. And that means a 350 volt unipolar system. And that means, okay, you have corrosion on the insulation, but not to the structure. So this is one of the key elements. But this is we need to define. But this topic on itself is a huge topic where we have to a separate webinar about. But Paolo, can you show me how a system look like?
Yeah, thank you, Harry. And this would be the picture of a current OS preferred system, which is TNS. And in this case, you can see that there is the plus, the minus, the midpoint distributed. And you see also the isolation, because we, in current OS, we separate AC and DC galvanically. And this is giving you a bit of a flavor how a prosumer installation would look like in under a current OS set of rules. So Harry was already presenting a bit all the possible arrangements. So current OS is, as I mentioned, TNS is the preferred approach. IT is can be done, even though there are other implications which are not, let's say, giving that the preference. And TT and TNC are not allowed for corrosion reasons. So this is just to give you a bit of a flavor how, because we know very well in AC how that works, but in DC you need to implement those systems in a different manner. But let me go back to a specific point, and I go back to you, Harry, because I was asking a question about 350 and 700. Those two values, can you explain why exactly those two values?
That's a nice one. Thank you for that question. Now, to give a small history. When you're defining an application, for example, if you are a caravan manufacturer and you want to produce caravans, and you have to select in your caravan a DC system, okay, then you want to prefer a 12 volt system, because all your small appliances are there, the small battery is there, it's working, all these things are working. So, and if you discuss, for example, with a distribution operator, network operator, they like to have 1500 volt because they want to save cables, they want to have high length to overcome, so they have a different driver for the 1500 volt. So you see that in both ends there is a push to define 12 volt or to define 1500 volt. But if it comes to application and different use cases of different installations, for example, if you want to charge your phone, okay, you will not have a 1500 volt system, because then the converter to charge your phone will be huge, complex and huge expensive. But if you want to run your vacuum cleaner or to charge an electric car on the 12 volt system, again, that converter will be huge complex and huge. So that means if you start analyzing in all the different applications into the system, from small homes to big homes to industry to greenhouses to distribution system, then you start looking to all the equipment, and you look to what is the preferable voltages for that equipment. For example, in a home, you have maybe the EV charger, you have the PV installation, you have a mobile phone to charge, you have USB-C sockets, you have LED lightings, all these small applications you have in a home. So what we did, we look into the PCB design in the past and looking, okay, what is the right voltages to design the PCB, to design converters. And we look also to the other requirements to the voltage. For example, what is the maximum length that you need to overcome in that use case? And what is the maximum voltage you can still have additional protection against electrical shock? Because if you take for 1500 volt, because we save a lot of copper, then we have to have a safety issue. So we look to all these properties and all these different architectures, and we look in the way that which voltage is applicable in the use case. And then we start to check all the boxes and look which voltages are possible. And then after we have done that, we try to find the common values, because in the end of the day, the same LED driver in a small home will also probably be used in office space or in a factory. Or if you have, for example, a motor or a van, it's running. So certain equipment need to run in different applications, and that's why you need to compromise, and that's why you have to select. And this compared to the different story, like to select with stay in the 1500 volt band, okay, then you have these possibilities. And what was important, maybe also to say something about that one, in the past we, for example, also started with 380. But when we're talking about 380 in our applications to installers, we quickly find out that the installer all the time thought we're talking about an AC system and not about a DC system. So that means to define the label, it's important to know what is is it AC or DC? So that we say, okay, in DC, the labels, the nominal labels, should not exist in AC. So that was one of the drivers where we come from. So it's a huge story. So that's why how this table is organized, and it fits into the use cases. So, and that's why we find that 700 and 350 are, in that case, the right one. But I want to say the label, what we all the time talk about the label, and the label is a little bit more than that one. So the label is actually bands. And Paolo, can you explain something about the bands? Because the voltage is just a number, but I think that the band is more important.
Yes, and I didn't add one dimension, which in when I touched about the bands, which is important, and which is time.
Yes,
because in the nominal band you can stay for an undefined time, but outside the nominal band you may have limits, because these bands are activated where you have transient, or you have changes in the state of the system, essentially. So there are bands where you can stay for a few minutes, but especially if you go higher, you need to limit the duration of those. So to a few hundreds of milliseconds, or even to a few milliseconds or microseconds. So this is really the second dimension. On top of the ranges, you have a time dimension, which is giving you a feel of how long the equipment and then the products which are connected to the system have to withstand a certain voltage. So this is an additional factor that we are sharing with you, so that you have let's say a more complete and comprehensive picture. And to continue on that side, on that line, we also would like to, maybe it could be interesting to understand what's happening outside current OS, because this is current OS, let's say, viewpoint and the set of rules of current OS. But there are others and other alliances which are working on similar things. So maybe, Harry, this could be a topic where you can bring some additional light. What's going on in other and similar alliances around the voltage?
Yeah, thank you, Paul. Yes, to explain a little bit, and I think this is huge good news what we have here on this slide, because we have a big fight in the market actually for the nominal value. But if you look to the definitions of all the systems in the world that are represented by organizations, actually they face the same technical challenges to define the voltage, the operating band of the system. So what is important is that, for example, U4, the definition of the temporary maximum voltage that could be there in the system for a couple of minutes, yes, that is globally almost everybody's agreeing on the same level. That means we have quite a consent about that level. That means the range how equipment operates in the system is here is actually already managed in the proper way. So from China, from the US, from Germany, and current OS. And the same is actually a little bit true for the U2 value, because the U2 value, there's some small differences, but the differences is not mainly coming from the definition of the voltage, but it is coming from how you define the voltages. Because if you define the voltage level for the source for the system, or you define the voltage as a range for equipment to operate on. So that means, so that then you have to talk about the warranty, you have to talk about the limits, what is applied to the system. For example, ODCA clearly talks about the operating limits of equipment. And while in current OS, we're talking about the system voltages. And of course, the equipment voltages should manage more than the system voltage, because otherwise you can never give warranty. So that is why actually we see that the 350 nominal, just a label. If you call it 700 or 350, or you call it 380, or you call it 650, actually is just a name. But the definition that belongs to the label, that is the most important one to have the full agreement on, and that makes the compatibility. And the interesting point is that actually current OS is quite compatible to the other alliances. So that means for equipment manufacturers, it could be more interesting to build for current OS equipment because it addresses the bands in the other applications. So this is why I think this is, from my point of view, this is very good news, and that's why I think that the DC topic, is close to be, how to say, enabling in a way that the market could be there, because we have a high consent on this moment on the voltage levels. So, Paolo, can you say something, because we will go to the Q&A after this one, but can you make something what we have just explained today and learned today?
I mean, just to, if we move to the next slide, Rafa, yes, exactly. So current OS is working on a number of different technical aspects, as we said at the beginning. And today we explored a bit more the voltage, because it's one of the fundamental parameters, and we explained a bit why we came up with certain voltages and bands. So we deem this is an important aspect, so we spend a bit of time on that. And I think here the message is important about convergence between the different alliances which are working on the same topic. There are other aspects which are we have them on the screen about current OS electrical rules. So we are working, and we will spend more time in the future with dedicated webinars to those. We covered already the DRUPs, the DRUP control approach in a previous webinar. I think the link is available, can be distributed to the recording, but there will be more to come on different technical aspects. So we recommend you to stay tuned and look for the next one. So now it's I think we have plenty of time for the Q&A. So we can check if there are curiosities or specific
thank you
aspects.
both. Prashant Group, who is a General Secretary of CurrentOS, will take your questions that you had in the chat. If you didn't have time to write because you were so absorbed, please turn on your cameras and ask them live. Prashant, over to you. Do you have any question at this stage, or maybe it's too soon and people are still...
No, there are many questions.
No, I have a few questions.
Wonderful, I cannot see that.
So I have responded, I think, a couple of them. First one was most of the DC converters can handle a range of voltages. Why bother standardizing? So I think that it was answered during the presentation, because this question came in the beginning of.
Maybe I can add a little bit more.
Provide some additional insights here.
Maybe, sorry, Paolo, maybe I can answer that one. Because of course it's completely true. Converters can handle a wide range of voltages. So why bother standardization? And that is true maybe for converters. But for protection equipment, for definitions on safety, on these kind of levels, there are other limitations in the system. Besides the electrochemical effects that you have to deal with in the system, you have to deal with the safety aspects. And of course, the converters can manage. But still, if you're looking to a converter and you're looking for a cost-optimized converter, the wider the converter can operate, the more expensive the converter will be. So if you make a converter that's suitable to operate between 200 volt and 1500 volt to be universal, okay, technically it's feasible, but that converter will never meet a low cost price. Of course, maybe it can be managed for a small auxiliary power supply like a phone charger, but to make, for example, an EV charger or to make other converters for other applications, that wide range, it becomes expensive. And that's why it is important to reduce the operating band of these converters, besides the rules that you have for the safety aspects and for the other effects that is defining the voltage. So it is not only the converter that defines.
All the elements of the system, because at the end, the system is not made only of converters. So all the elements which are connected in the system.
Yes.
Okay. There was also a question about US class 4 FMPS. So the question is, do you see some room for US class 4 FMPS standard to be adapted in future in Europe?
You take, Paolo?
This is the fault managed,
yes,
if I get correctly the question. So there is some discussion already ongoing about this between CurrentOS and some additional players. So it's an ongoing topic, I would say. So the discussion is ongoing on that one. And by the way, just let me comment that the question is specific with a specific spin to Europe, but CurrentOS is not Europe-centric, because CurrentOS has members globally. So we have members in North America. We even have a dedicated North America committee, by the way, within the foundation. We have members in Europe, but we have also members in Asia. So we are truly looking at this topic from a global perspective. So just as a complementary note, because I saw the spin of the question.
Maybe I can add a small note to this one, is that I understand the question quite well, because this application has a huge benefit in the US, because you can avoid the plumber. How to say? We call it in Europe, we call it plumbers. From the electrical piping, the tubing inside buildings. But in Europe, we have different requirements inside buildings. So that I think there will be a use case and there will be a value, but it will be a different one than in the US. So that is why I think there is place, but maybe on different type of applications. So.
Okay. Thank you. And there is also a question on dedicated protection switchgear for DC. Will it become more expensive protecting DC systems since current doesn't hit zero, or does the overall system reduce cables, as I saw in this slide, become almost same or less expensive than AC system?
Okay, so this is a pretty wide question, and maybe going beyond scope of this webinar. We may need to have a full webinar to answer this question. I mean, DC current doesn't need zero. This has always been the case. So the historically the challenge in protecting DC has always been there. Just to comment quickly, CurrentOS has a specific approach to this topic, dividing the installation in different zones, and depending on the characteristic of the zone of the installation, the part of the installation, there are different protection requirements. The advantages of adopting DC are, I mean, well known, and you can get savings in the cable sizes. You can get savings in the losses. So it's definitely outweighing other considerations. So it is maybe demanding or requesting a full session, a full webinar. This one.
Yes, it's because zoning is a topic on itself.
Yeah,
so there's so many different type of protection definitions for DC, and some of them are more expensive, and some of them are also still more expensive, but different. Yes. Yes.
Okay, good. Thank you. Jim, you had raised your hand.
I see a hand of Jim.
Yes.
Yeah, hi guys.
So go ahead.
Good morning from 7 o'clock in Boston. So thank you very much for
morning.
having the meeting slightly in my time zone is perfect. So thank you very much. I feel special. My California friends are really out of luck on a call like this. So I feel very responsible to represent them as well. Yeah, so I'm working on the U.S. energy codes, and I have an opportunity to introduce DC as a sturdy alternative with efficiency in mind. And one thing I'm worried about that I'd like your help on is Harry's chart about the voltages and the different use cases. That really helps communicate things. Charts like that are helpful. Another chart might be the pragmatic review of the safety standards for the major regions that you're targeting to see what standards are still in question, what might be in work still. Where are the sticky points that maybe a code cycle from now will be resolved, but isn't quite ready yet. So the idea of it, this is inevitable, right? Physics is our friend, and so we need to keep moving this forward. But this battle will have many fronts, and one would be in the standards organizations in the different regions you're focusing. So could you please consider making a chart, or maybe a whole baby webinar on the standard side of this? I think that would be very helpful.
Sorry, maybe Jim, but there's one thing because I think you hit a very sensitive topic, and we have a little bit the same type of discussion in the IEC. Is that if you say, for example, 350 volt, what does that mean? Besides the operating band, what does that mean? Is it TNS? Is it an IT? Is it 175 volt against PE? Is it a symmetrical system, asymmetrical? And that is not proper defined. So you see many tables in the standardization about voltages that they say, okay, you can protect up to this voltages, but without an explanation, it's the line to line, it's the line to earth, these kind of topics, and that is still a way to go. But that's why I want to say is that CurrentOS, we make it very clear how it's defined, and we're working on the protection schemes to make it feasible and to make it safe with the full definition. And that's why I think, in the end of the day, I think CurrentOS should be, written in the NAC or written in the IEC, IEC in this case.
And that takes a lot of not politics, but just good argument making with the different organizations and being steady about it. Yeah, thank you for that. I have another question, but I would take more of an answer if you wish. That's fine.
So maybe as an additional comment, Jim, to your question, that's also, what you ask and the specificities of different regions is why we organized ourselves with a dedicated North American committee, because there are specific considerations and in North America that we want to address through the North American committee, just to complement.
Yeah, that's great. Thank you for being careful and thoughtful about that.
And maybe one thing, one thing to add on that one, because DC is the last chance in the system to harmonize globally on the system. So that's why we should try to prevent too many regional barriers, because we need to compromise there also in the same way to make this consent, because the same what is happening in USB that could also happen in DC. And that is our last chance, because I don't know yet another method to have electrical energy transfer, something like in between AC or DC. That's new. But so I think we should very strongly aligned on this global approach.
Thank you. My next and last question at this point might be this idea of when protection and DC. At the moment, at the maturity level of the equipment, there might be, unfortunately, a cost increase in how to deliver power to a building because of the protection, the maturity of that equipment. I think it'd be helpful if you took maybe 2 or 3 use cases that are your best shot at cost unity and actually do the math on where where today's prices are on certain equipment, and then help illustrate how it may not be cost effective yet, but it should be. To be really face the cost difference question head on would be very mature. Thank you.
Okay.
Hello.
So well noted, Jim. And I think that itself is another webinar. So it's a very good topic.
Yes, and I think in the background, but that is on the company level by each Kernel OS member. Everybody's working on these kind of applications to defend the rationale to move to DC in that case, because everybody's looking for the business case in certain installations. But one thing I want to add one, visionary topic on this one, because we talk about the system change. And to change the system, that means we have to redefine the business cases in the system, because when you change something in the system, somebody loses, somebody gains. And if somebody is losing, is blocking this transition, then maybe the society will lose value. So that's why the system approach is still key. And when things scales up, then price will be becoming a different argument. But to block topics from day one just on price and the business case, it's very difficult.
To show.
That's sorry.
Okay. Yes, I have few more questions. One is on within the context of stationary batteries supporting DC microgrid plus increasing penetration of high voltage, including EV batteries. Do you recommend battery manufacturers to also adopt the proposed voltage standardization?
Close. I should not be the same, because maybe the funny thing is that AC was actually derived from a winding, from magnetic. So you have the winding turn ratio to make any voltages. And DC is actually derived from chemical effects. So there is no rotating topics inside. And batteries are always, the key devices who defines in the past DC voltages. And but I think, to be honest, that batteries in systems, not in applications, but in systems, probably will also always behind the converter. And if they are behind the converter, then the battery voltage is not so relevant in that case. Of course, if you want to optimize the converter, if you want non-isolated converters, it could be handy to have the battery close to the system voltage to decrease the cost of the converter. But if you're an isolated converter, then it doesn't matter actually so much in that case. It's and so the system, and that's why in the IEC we define active and passive systems. And in the passive system, what we say that you have the batteries connected to the system, then the voltage band is based on the chemistry of the battery, not so much as a controllable state. And if you have an active system, that means you have only converters to the system, then the system is defined by the operating of the converters. So that has a different band behavior. And the chemistry is very difficult because once you have LFP or you have LMC, you get different, operational bands on the chemistry. And if you have maybe in the future another chemistry with a different curve, you can again. So this, I think chemically wise, it's very difficult to standardize the voltages for batteries on that level. That's a personal opinion, how to say. Yes.
We have time for a few more questions.
So I have one more in the chat, which is, could you please tell us a bit more about CurrentOS and how it differs from associations such as ODCA?
Okay.
This one is for you, Prashant.
Yes. So, so it's yes. So CurrentOS is a foundation created, and we are more focused on buildings and installations. DC installations, like it could be parking, it could be even we have some applications or use cases of data centers, and most of the other I would say associations are created by region. So if you look at Emerge Alliance, this is an association created specifically for DC in US. The CABI or PEDF is an association created in China. We have only two associations which are both located or created in Europe. One is CurrentOS and another one is ODCA. The major difference is that ODCA is created by the industries, DC industries, and it focused more on the industries. So applications within the industries, within a factory, how to optimize the application within the factory using DC. And CurrentOS was more focused on building application.
But nevertheless, we have for 3 years bi-weekly meetings to harmonize, to prevent that we depart from each other, how to say. So that's a lot of effort.
Maybe. And our objective is to converge with all the associations, and this is why we are connecting with all the associations, and we are having regular connection to bring everyone on the same page and work together.
Yeah, and maybe the additional consideration we can also add here, beside what you already stated on collaboration and the convergence efforts, is CurrentOS, beside let's say the technical work, has also established a certification scheme, which is helping all the manufacturers to verify with third parties the compliance with the set of rules. So this is distinctive of CurrentOS and maybe worth mentioning here, because the question was about the differences.
Yeah, thank you, Paolo. Very good point. Yeah, exactly. Okay, I have again, Jim, you have one more question.
Yeah, I see one question, new question. How communication will be handled between devices? Is that part of CurrentOS? That's the last question I see.
You
said Prashant, Jim had another question. We have time for both, I believe. We can.
I liked his question better, so I thought you'd.
Okay.
So any of you want to take it? How communication will be handled now between devices?
Maybe I can answer. Now, the most important thing what we define in CurrentOS, that the communication is actually done by the voltage. That means the voltage is used as a signal to do the fast time domain communication. And to come up with a communication standard today, yeah, that is very, how to say, things change very fast in communication technology. It could be MQTT, it could be Modbus, it could be, there are so many different protocols and they are changing. So it is still an open topic. It will be incredibly good to standardize that one on equipment, but I think that we're focusing now on the communication aspects based on the physical, on the voltage as a signal. So that is one of the key elements. And I think when there are more experts in the organization that can contribute to develop more on the communication standards, yeah, that could be. I think that is for me. It's more an open point, but that I answer for myself now. So I have to say, not as an organization.
Yeah, maybe said in a trying to say that in a slightly different manner. You don't need a central controller talking to all the devices to make the system work, because every piece of the system is just looking at the voltage and using that voltage, which is as a consequence of physics, to as a signal to determine their behavior. So that's the distributed control approach that CurrentOS is taking. Just to complement or try to give an additional element to the answer from Harry.
And you can also go to the previous webinar, which I posted the link in the chat, and you could look at it, how the group control works. And this will give you also some idea about how we manage the decentralized management of power.
Yes, all our webinars are posted on our YouTube channel. You can also find them, and this one will be on our YouTube channel, CurrentOS on YouTube, and you get all the webinars.
Go ahead, Jim.
Thanks. My last question might be this idea of isolation as a philosophy. And if you could bring up one of your pages here that has one of your general purpose diagrams, could you describe where your basic isolation schemes are, how that is kind of integrated within the protection mentality or philosophy you have? And then are there opportunities for additional isolation layers that are required for safer applications? Like, is there a certain risk balance that you're trying to take with your current isolation, your basic isolation scheme, let's say? Are there opportunities for even safer systems?
Paolo, you take?
So I guess you're referring to the schematic which was shown during the first part of the webinar. We decided to go with isolation between AC and DC. This is the main thing, because we don't want to have faults happening on the DC propagating and involving the AC. So we really want to decouple the two sides, and that's the main isolation we are referring to. In the system reference document, there are other converters which are typically recommended to be isolated. So it is developed, and you have an indication of the isolated converters which are recommended depending on the. Now I don't recall by heart, Ari, if you have maybe your memory is better than mine, but there are other places in the system where we recommend isolated converters.
Maybe to add a little bit on that one, we do by default isolation to AC and DC because exactly what Paolo said. We don't want to have the effects on both systems. We want to have DC faults in AC system and other way around, AC faults in the DC system. But we do isolate, actually one of the common rules that we do in isolation. When you make a big voltage step, for example, you go from 700 to 350, then you shall isolate.
Please,
because then you shall isolate. But if you make a small step and you stay within the voltage bands, then it's not necessary per se to isolate. So that's why if you go to 48 volt, for example, okay, then you shall isolate because you provide a self-low voltage from a DC distribution system. And that is how it's defined. So that's why if you look into more details to the U1, U2, U3, U4, U5, U6, they are actually guiding you through the process when you need to do isolation or when you can stay without isolation, because you need to manage the maximum possible voltage from a non-isolated converter in a proper way. That's how we have strong rules for that one.
Thank you.
And I think it's a wrap if there are no more questions. Thank you to both our hosts, Paolo and Harry, who prepared this dialogue for you, and Prashant for being here, always supporting the development of CurrentOS. You will be able to receive this webinar, or if you don't receive it in time, you will find it on our YouTube channel within a few hours. I will post on LinkedIn as soon as the recording is ready. Thank you for these amazing questions, and see you hopefully in our next webinar very soon. Within a few weeks, there should be another one. We are working on it already.
Yeah. Thank you all.
Thank you.
you.
Thank you all for
everyone.
being here.
See you. Bye.
Bye.